is okay, one second. Yeah, the session C. I was not able to record in one full video, so it's about the harmonics produced in a stretched string. Consider this is a stretched string. You have something like this. This is L, entire length L, in which you have a node here and a node here at both ends. So when you have one full wave is like this, a node here and a node here. This full wave is lambda. So this is just half of it. Can you see this node here and a node here shows that's just half of this wavelength. So the entire length of the tube in the first case is made up of lambda 1, considering lambda 1 is the entire wavelength. So lambda 1 by 2. Okay, and therefore lambda 1 is equal to 2L. And the whole point is to find the frequency. Frequency is equal to mu is equal to c by lambda. C by lambda, or in other words velocity by lambda. You should know this. The frequency is equal to velocity by lambda 1 in the first case. And lambda 1 itself is 2L. So frequency itself is V by 2L. And V is already equal to the T by M, tension by mass per unit length of the string. The velocity of a stress string is directly proportional to root of the tension in the string by mass per unit length. So substituting that value here, mu is equal to V by 2 into 2L, and instead of V you write root of T by M 1 by 2L into root of T by M. So thus this is your frequency 1 when considering for this diagram, and this is known as first harmonic, or first harmonic is also known as fundamental frequency or fundamental note. So let's call it first harmonic. So next let's go to second harmonic. And for producing a second harmonic, you have to similarly you have to have a node here and node here, an extra node here. The same length of the tube has got 3 nodes in total. So the entire length L, and this is equivalent to one full wavelength. So entire length of the tube has got a wavelength lambda 2 in this case. And mu is equal to C by lambda. So mu is equal to V by lambda 2, where lambda 2 itself is L and V is equal to root of T by M. So 1 by L. So for consistency's purpose, since you have a 2L here, you can multiply and divide this by 2. So that this will be a second harmonic. This will be your second harmonic, or in other words, it's called the first overtone. First overtone. Okay, next mu 3. Same stretched string, you're going to have 1, 2, 3, 4 nodes. So then from here to here is one full wavelength, from here to here is half wavelength. So wavelength 1 plus 1 by 2 will be 3 by 2. The entire length of the tube has got 3 by 2 into lambda 3. Thus lambda 3 itself is 2L by 3. And frequency is equal to V by lambda 3. Lambda 3 itself is 2L and a 3 here. And the velocity itself is root of T by M. And you already have a 2L, so no need to multiply and divide by 2L. Thus you get 3, this is known as the second, this is known as the third harmonic, or the second overtone. And thus you got, can you see, this is equation 1, mu 1, this is mu 2, and this is mu 3, and mu 1 is to mu 2 is to mu 3 is in the ratio 1 is to 2 is to 3. That's all proved. So this completes the question, this section number C in this, okay, section number C. So in 33rd question, let's go to 32nd question. Hope it's recording. Yeah, it's recording. Okay, 32nd question. State Bernoulli's theorem. Bernoulli's theorem. What is Bernoulli's theorem? P plus half rho V square plus rho GH is always a constant. Pressure, they say the pressure. So this is the pressure, this is half rho V square, which is the kinetic energy, and this is the potential energy. So then they say the pressure energy plus kinetic energy plus, the pressure energy plus kinetic energy plus potential energy per unit volume of an ideal fluid. is always a constant. So that's what it is. A pressure energy P plus half rho V square plus rho GH is a constant, or in other words, a pressure energy plus kinetic energy plus potential energy of a fluid per unit volume of an ideal gas is always a constant. Or in other words, the velocity increases, the pressure decreases, the pressure and that's what it is, and because it has to remain constant. This is what is Bernoulli's theorem. So then after that is that's section A, state Bernoulli's theorem. So A is being answered. B, with the help of suitable diagram, derive Bernoulli's equation of a liquid flow. So to derive Bernoulli's equation, you have to draw something like this, yeah. And you have a fluid which is moved from here to here, whereas here you have a fluid which is moved from here to here. This will be V1 into delta T with the distance through which it's moved. It's V2 into delta T is the distance this is moved. Then this is being the area of cross section, and you know there will be a pressure P1 on this and there will be a pressure P2 on the other side. There will be a pressure P2, the pressure with which the liquid is going to flow out, or through the flow in the tube. So that's a pressure V1 delta T, V1 being the velocity here. You know that the same volume, the volume that's flown through this distance is equal to the volume at this distance, because it's taken the same time delta T. And ideal, we are considering it to be an ideal fluid which is incompressible, and the density is a constant, and there's no friction, there's no viscous force. These are the conditions for an ideal fluid. So using a situation of an ideal fluid, we're going to derive Bernoulli's, where how you should start is work done. Okay, the net work done is equal to change in kinetic energy plus change in potential energy. Net work done is force into displacement, and force itself is pressure into area into displacement. Okay, so then therefore the pressure difference, the net pressure difference between the left hand side and the right hand side, okay, or so then therefore the pressure difference is, let's consider left hand side pressure is P1, area is let us consider the area to be A1 here, area to be A2 here, not capital A. Okay, so the area will become A1. The distance through which it's moved is V1 into delta T. Is the pressure on the left side minus pressure on the right side is P2 into area is A2. The distance is V2 into delta T. Is the net work done, which is equal to change in kinetic energy, which will be half m V2 square. Right hand side kinetic energy minus left hand side kinetic energy, which is half m V2 square minus half m V1 square, plus change in potential energy. You know the height is, this is H1 and this is H2 from the surface. So the potential energy from the right side is mg H2 minus mg H1. So this is what you should write, and in this statement it's half into mass on the right side. It exists with V2. The mass is always density is mass by volume. Mass is density into volume. Density is the same everywhere. The volume on the right hand side will be A2 into V2 into delta T into V2 square, and this is V2 square, minus half into, again the mass on the left hand side is density into volume, which is rho into A1 V1 delta T into V1 square, plus mg H2, which is the mass on the right hand side, which is density into volume. Density into volume on the right hand side is A2 V2 delta T into G into H2 minus mg H1 is m on the left side is density into A1 V1 delta T, A1 V1 delta T, density into volume into gravity into H1. So you have the left hand side, you have P1 A1 V1 delta T minus P2 A2 delta T. You have this on the right side. Okay, and you know, since A1 V1 is equal to A2 V2 by theory of continuity, for an ideal fluid, A1 V1 delta T and A2 V2 delta T are just the same, because A1 V1 is A2 V2. So A2 V2 delta T, A1 V1 delta T, A2 V2 delta T, A1 V1 delta T throughout can be cancelled. So you'll be left with P1 minus P2 is equal to half rho V2 square minus half rho V1 square plus rho G H2 minus rho G H1. Okay, taking all the ones to the left hand side, P1 plus half rho V1 square plus rho G H1 is equal to P2 plus half rho V2 square plus rho G H2. Thus, a P plus half rho V square plus rho G H is always a constant. always a constant. You can say the pressure plus pressure energy plus kinetic energy plus potential energy for unit volume of an ideal gas is always a constant. So then that's what it is, and this is how you derive Bernoulli's with suitable diagram. Give any two practical application of it. The application we have learnt about Torricelli's reflex. We have learnt about Venturi meter. So then those are the two applications. Torricelli's. Okay, two applications of it. Okay, we derived Torricelli's reflex using that. Torricelli's reflex is based on Bernoulli's, and similarly Venturi meter. Venturi meter helps us to find the rate of flow of fluid from a tube. And Torricelli's reflex is like there's a tank. What is the rate of flow fluid from the efflex, the small outlet pipe. So these are the two derivations which we learnt, where we used Bernoulli's. And there are many other applications. I don't know which application they want. They want practical application. These are all derivations, applications on derivations. The practical applications in our daily life is, I've told you that basically an atomizer. An atomizer is an example. Atomizer, then dynamic lift, that is the Magnus effect, and the aerofoil. These are all the practical application. In an atomizer, you have a horn, auto horn kind of a thing. When you press it, there will be a pesticide here, and when you compress this, the air rushes out, thereby causing a low pressure here. So then there will be high pressure here, because of which the fluid will get it moves from high pressure to low pressure, and thus you can spray it. The fluid moves from high pressure to low. That helps you to understand, again, that is based on Bernoulli's, the application of Bernoulli's. So you better don't say Torricelli's effects and Venturi meter. A practical application you can say is an atomizer, and also you have told you Magnus effect. Magnus effect, where when you're going to spin bowl a ball, you're going to do a spin bowling, it drags a layer of air above it with it, thereby creating a low pressure, because of which air from the front moves back from high pressure to low pressure. And so what is causing on the top, you see the ball is moving forward, but the air is getting pushed backward, and so the resultant velocity decreases. Resultant velocity drops. When the velocity drops, the pressure increases. Whereas at the bottom, if you see, the air is getting pushed back and the spinning is also happening in the same direction. So resultant velocity increases, and so the pressure decreases. So there's a low pressure at the bottom and a high pressure at the top, and therefore the ball gets spinned, it gets pushed down in not exactly a parabolic trajectory. It takes an unexpected curved path of the spinning ball, and that's known as Magnus effect. And I'll tell you the next application is an aerofoil. Aerofoil, the wings of the aircraft is designed like this. So when the aircraft is moving forward, it takes away an air layer with it. It's causing a low pressure here. So the air from the front moves backward like this. And here it moves like this. But if you see, because the area is smaller, area between the layer is smaller, the area is less, the velocity is more, because AV is a constant in theory of continuity, and then the pressure becomes less. Thereby there is a low pressure on the top, and there's a high pressure, because here the area is more, velocity is less and the pressure is more. There's a low pressure at the bottom. So there's the high pressure at the bottom. Pressure is high. So high pressure, air moves from high pressure to a low pressure area, and thereby pushing the wing up. And the designing of it is known as aerofoil. The designing of the wings is known as aerofoil, and these are all based on Bernoulli's application. So that completes it. The next question is an OR question, which I want to discuss. OR. What is capillary? What is capillary? Give two examples of capillary from daily life. Derive an expression for ascent of the liquid inside the capillary tube when it's dipped in a liquid with appropriate diagram. So, the rise of a fluid in a thin tube, the rise and fall of a thin tube, or spontaneously or all by itself, is known as capillary. The rise of a liquid due to surface tension, these are the keywords, rise of a liquid in a thin tube due to capillary action, due to surface tension, is what is known as capillary rise. So that is capillary rise or capillarity. So the phenomenon of the rise of the liquid in a thin tube due to surface tension is known as capillarity. Give examples. Okay. So the practical life examples that you can talk about is the ink rising in the pen. Ink rising in pen is due to capillary action. Then another example you can talk about capillary is the water from roots goes on to the leaves, goes into leaves of the plant by capillary action. So that explains 2 examples in daily life. Let's go to C. Derive an expression for ascent. So let's derive an expression for ascent. You take a thin tube like this, and it is so thin, the tube is thin, but I am showing it like this. So it is so thin that you can imagine that it's going to form a kind of a sphere. It's going to be so much concave that it will form a kind of a closed sphere. So where you have this to be the radius of the tube, while capital R becomes the radius of, capital R will be the radius of the bubble. Supposing, okay, let me draw it properly. So from here to here is capital R, from here to here is small r, which is the radius of the tube. Capital R is the radius of the sphere of the bubble. And so then this being theta, because you know this is theta, this is also theta, and just make it into a right triangle. And can you see that sin theta, cos theta is equal to small r by capital R. So write this, from this triangle write what is cos theta's expression. And you know the excess pressure inside any bubble as in a liquid droplet is 2 sigma by r. You should know this formula. The excess pressure is P is equal to 2 sigma by r. And so then where r is this, which is the radius of the sphere, and here r is equal to small r by cos theta if you cross multiply. Substituting that here is 2 sigma by small r into cos theta. That will be the excess pressure. The pressure is also rho g h. Pressure is also simply h rho g for the ascent, correct? So replacing h rho g here, 2 sigma cos theta by r, from which you can find the ascent, which is stands for h, which is 2 sigma cos theta by r rho g. Thus you get the formula for ascent, which is this. Okay, so that completes ascent derivation. Next. So the next is the 31st question, in which I'll answer the or part. Define radius of gyration. So radius of gyration, you know, just draw this and consider this to be m1, another mass m2, which is a distance r1, r2, m3, r3, and another mass mn, which is the distance rn. This is the axis of rotation. Consider lamina, which consists of particles m1, m2, m3, which is a distance of r1, r2, r3. So then let's do the derivation for radius of gyration. It's you know, moment of inertia is m1 r1 square plus m2 r2 square plus m3 r3 square plus dot 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 mn rn square. And now considering the masses, this is the net moment of inertia, considering all the masses are same, is m into r1 square plus r2 square plus r3 square plus dot 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 rn square, multiplying and dividing it by n number of molecules, considering it. So it will be capital M, nm is capital M, r1 square plus r2 square plus r3 square plus dot 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 rn square by n, where you know moment of inertia is mk square, therefore k square stands for this whole thing. Therefore k square is r1 square plus r2 square plus dot dot rn square by n. Therefore k is equal to root of r1 square plus r2 square plus dot dot rn square by n. And from this is known as radius of gyration, and from here you can derive it. It is root, this is square root, root mean square. Okay, there is a mean and a squares. So then root mean square values, or root mean square values of all position vectors, position vectors of all position vectors about the axis of rotation, about the axis of rotation. So this root mean square r1, r2 are the position vectors of all the particles there. So root mean square values of all the position vectors of particles about the axis of rotation is what is known as defined radius of gyration. That's done. Name two factors it depends upon. Radius of gyration, obviously, and it depends upon how the how radius of gyration depends upon. Can you see from here the way the particles have been distributed? சொல்லுங்க வெங்கடேஷ். ஆமாம், நாளைக்கு சார் வந்து ஆமாம் இன்றைக்கி 1 மணிக்கு வந்துடுறாரு. நான் நாளைக்கு வாங்கி வச்சுக்கிறேன் ஷூராக. சரி சரி. ஃபீவரா? ஐயோ, எல்லா இடத்துலையும் இருக்குது. ஆமாம். சரி சரி சரி. இருக்கு. சரி சரி. டேக் கேர். சரி வெங்கடேஷ். சரி சரி. 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 ஆமாம். சரி வெங்கடேஷ். சரி. ஓகே. இன்னைக்கு 1 மணிக்கு வந்துடுறாரு. நான் ரெடியாக வச்சுருக்கேன் கேஷ். அவர்கிட்ட கேட்க வேணாம், நான் தந்துடுறேன். அப்புறம் நான் வாங்கிக்கிறேன். சரி வெங்கடேஷ். தேங்க்யூ வெங்கடேஷ். Okay, so I hope this recording was there. Okay, so then mass has been given, length has been given, a moment of inertia is formula is given, but you know moment of inertia is mk square. So equating, you get this. Just substitute and leave it. Okay. So next is yeah, it's recording. I hope it's recorded everything. Next is derive an expression. Define angular momentum. That's 31st question. Define angular momentum. You know, angular momentum is represented by L, and I've drawn this diagram. Angular momentum is r times linear momentum. And suppose you have a particle here which is at a position vector r with m here. You know, mv is the linear momentum, is r cross p. L vector is equal to r cross p. It's a cross product of position vector and the linear momentum. This is known as angular momentum. So define an angular momentum is a cross product of the position vector and the linear momentum is what is known as an angular momentum. So that completes it. And derive a relation between moment of inertia and angular momentum. Moment of inertia and angular momentum. Moment of inertia is I, which is mr square, and angular momentum is L, which is r cross p. And you know, this itself is moment m into v, which linear velocity itself is r times angular velocity. So thus you get m r square omega, and mr square itself is I. Thus you know, this is how you derive the derivation between angular momentum and moment of inertia. But this same thing they've asked for n number of particles. So if it's n number of particles, you just have to write this as r1 into r1 cross m1 v1 plus r2 into m2 v2 plus r3 into m3 v3 and so on. And then considering that m1 is equal to m2 is equal to m3, you can take m out. It's r1 cross v1 plus r2 cross v2 plus r3 cross v3 and so on. And you know, linear velocity is r times angular velocity. So r1 r times angular velocity. So plus r2 r cross p square omega. So r2 into r2 omega, the angular velocity will always be the same. For a rotating body, omega is always going to be the same. So then omega 1, and so this also not omega 1, it's just omega. So can you say m, therefore it's r1 square omega plus m r2 square omega. Okay, taking it inside, it's m r1 square omega plus m r2 square omega, and mr square is I1. So I1 omega plus I2 omega plus I3 omega. And so then therefore this is you can also write it as I omega where I is equal to 1 to n. So something like this. Okay, you can just manipulate and write it for n particles. So next question is main is this. If you had written this, it's fine. Okay, it's just that for n particles you need to change it. The maximum and the minimum distance of a comet. Okay, let me do this sum. So let's do this numericals. The maximum and the minimum distance of a comet from the sun. Let me draw the sun. Maximum minimum distance. The maximum distance being 1.4 into 10 to the power 12 meters. The minimum distance being 7 into 10 to the power 10 meter. If the velocity nearest to the sun, if the velocity at this point nearest to the sun has been given 6 into 10 to the power 4, what is the velocity farthest when it's far away? Angular momentum is always conserved. So then angular momentum is conserved, and so the angular momentum here should be equal to angular momentum here, which is r times linear momentum, which is r1 into linear momentum, which should be equal to r2 into its linear momentum. r1 is a position into mass into velocity v1 should be equal to r2 into mass is the same, the velocity v2 will be different. Because it's the same, that's going to be nearest and farthest, so m and m will get cancelled. So r1 and v1, which is 6 into 10 to the power, r is 7 into 10 to the power 10 into velocity 6 into 10 to the power 4 is equal to r2, which is 1.4 into 10 to the power 12. And the velocity v2 is what they're asking. Just strike this off and bring this down and do the calculation, and that will give you v2, which is in meter per no, it's in meter per second. Yes, so that completes the section D. With this, section D is complete. Okay, so next is session C, which I'll do a separate recording.